So this screencast will review exam 3, which was the module on conformational analysis, acid-base chemistry, and stereochemistry. So compound 1 is asking you what are the functional groups present in albuterol, which is the structure shown. So here we have the primary alcohol. Here we have an aromatic alcohol called a phenol. We have a secondary alcohol. And then here we have a secondary amine. So the correct answer for this one looks to be B, primary alcohol, secondary amine, and phenol. So how many unique sets of hydrogen are present in albuterol? So we'll go ahead and change the pen color here and just identify them with green. So we have this H, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then the methyls are all 1, so that's 11. So what is the pK of the most acidic hydrogen in albuterol? So from question 2, you realize there's 11 unique sets of hydrogen. And so what you're doing is identifying what functional group those sets belong to, and you use the information really from question 1 to help you out with this. So you can see that there's these alcohols present, and they're going to be the most acidic hydrogens of all those functional groups. But you have 3 types of alcohols. The aromatic alcohol is the most acidic one, and that has a pK of about 10. That was the phenol. And that can be found in the table in the prior exam pages. So question 4 relates to the fact that you have 3 alcohol hydroxyl groups, but the phenol is more acidic. And so the correct response for this one is A. So this has to do with the resonance stabilization of the resulting phenoxide that's formed, and we talked about that in lecture. So question 5 is basically asking you, if you treat albuterol in 4 different experiments, which base is not going to establish a product favored equilibrium. So that's essentially going to be answer A, because this is going to generate acetic acid as the conjugate acid of that base. And so if you're looking to fully deprotonate one of those hydrogens, you have to use a base with a delta pKa value that's going to favor that product equilibrium. So if you look at the remaining ones, sodium hydroxide, sodium methoxide, and the acetylene anion, those will all have a delta pKa of 10 or greater. So they're definitely going to push the equilibrium to the product. Number 6, if albuterol was treated with 1 equivalent of sulfuric acid, which functional group would be protonated? The correct answer is the amine. And again, if you look at the periodic table, CNOF, we know that basically acidity increases this way, so basicity increases that way. Really, we're comparing the amine functionality versus the alcohol functionality and what is acting as a base. So the amine is going to be the thing that is protonated, and that's relating to question 7, what is the mechanism for how that happens? So the amine is 8, so our sequence starts with 8. 1 is the acidic proton of the sulfuric acid. So we have to do 8-1 in terms of drawing the arrow, and then we're breaking 2-3. So the correct answer here was A. So that's forming this ammonium salt, which I'll just use that for the rest of the molecule, the nitrogen plus, then you get the counter ion here. So the reaction arrow is going to look like A, because sulfuric acid from the pKa table has a pK of -9. This conjugate acid on this side, this ammonium, we said has a pK of about 10, and the equilibrium lies towards the weaker acid-base pair, so our arrow is going to look like A. The charge on the heteroatom of nitrogen is going to be +1. In consideration of the protonation of albuterol by action of sulfuric acid, what is the overall net charge? That's going to be 0. We have a plus and a minus. So again, we don't have an offset of charges. They cancel each other out to get 0. How many stereogenic carbons does albuterol have? It has 1. So there's the stereogenic carbon. Remember, this word means 4 different substituents. If it has 1 stereogenic carbon, there's 2 total stereoisomers. So again, we're using 2 to the n. We said n equals 1, so 2 to the 1 equals 2. That means those stereoisomers are R or S. Albuterol is sold as the racemate. What is the composition of enantiomers? So that's a 1-to-1 ratio. That's what racemate means. This next question is asking you, in a commercial sample of albuterol measured in a polarimeter, what's the expected specific rotation? So again, it's a racemic, so it's going to be 0. Which of the following molecules correctly depicts the S isomer of albuterol? Again, we have to use the Kohn-Ingold-Prelog notation. So we're looking at the stereogenic center there. We find there's an oxygen, a carbon, and a carbon. The hydrogen here is the lowest priority. It's pointing out towards us. So of those 4 atoms, oxygen gets the number 1 priority. Hydrogen coming out towards us is number 4. But then we have carbon versus carbon. The carbon on the left has a nitrogen, so that gets the 2nd priority. This carbon gets the 3rd. We're going in a counterclockwise fashion, but since the lower priority group is pointed towards us, instead of being S, that is R. B is also R. All we did was a bond rotation about this bond from question or choice A. C is the S isomer. That's the correct one because you can see we've inverted from the dash to the wedge. And D is just basically flipping molecule A over and looking at it from a different perspective, so that's also R. So C is the correct answer for this one. So this next question is saying that albuterol is sold as a racemate. However, the pure R and the pure S enantiomers, if you have them, they will racemize. So R will form a racemic mixture, and pure S will form a racemic mixture. So this question's asking you, how does that mechanism happen? Well, basically, the nitrogen's already protonated, and the stereogenic center is the secondary alcohol. So we know that if something is to racemize, it has to be the center that's with the 4 different substituents. So the correct explanation here is B. The secondary alcohol is protonated by the acid, leading to an intermediate that resembles a hydronium ion. So you don't need to know what the exact mechanism of this is. You just have to recognize that the functional group of being the secondary alcohol is the carbon of the stereogenic center. So if that's pure R or pure S, that's what gets racemized. So 17, which molecule has a singlet in the proton NMR? So the thing with this is 3 of these names are totally incorrect. So 1-dimethylmethane, that's essentially propane. 2-methylene ethane, that's propane as well. 1-methylethane, that would be propane. So those names are incorrect. They all lead to propane. It's asking you a singlet. So there's propane, there's 2,2-dimethylpropane, so that has a singlet in the proton NMR. So those are not correct because they're not going to have the right criteria for the question, and additionally the nomenclature is wrong. So what is the name of this molecule? It's given to you in a Newman projection. It's basically a butane derivative. The easiest thing to do is just draw it in the anti-fashion. If you're unable to do that visually, a model kit will help you do it. And then we prioritize the groups. Bromine gets 1, this carbon gets 2, this carbon gets 3, hydrogen is 4. It's away from us. We're going 1, 2, 3, so that's clockwise. This is going to be R, 2-bromo, 3-methylbutane, so it's B. 19 says, which of the following is trans? 1-tert-butyl, 3-methylcyclohexane. So here's cyclohexane. We have a tert-butyl at the 1 position. We have a methyl group at the 3 position. Those things need to be trans to one another. And so if we're looking in the chair conformation shown, A is not correct because it shows a 1-4 relationship. B is not correct because it's also showing 1-4. So we choose between C and D. C is cis, D is trans. We need the trans configuration, so D is the correct answer. So 20, which of the following converts to flat cyclohexane? So the tert-butyl group needs to be equatorial because it's the biggest group. We can eliminate A and B. And again, that's based on the A values that we learned. So now what we need to consider is the relationship of the tert-butyl relative to the other methyl groups. So the one right next to it has to be trans. So we see that basically here and here, here and here. So then we look to the other methyl group. It has to be cis to the tert-butyl, so C is the correct answer. You can see this one here, and D is trans. So D is not correct. 21 is asking you about the correct answer from 20. And what is the coupling constant between HA and HB? Both HA and HB are axial. So their dihedral angle is equal to 180 degrees. You can go on the chart at the front of the exam and look at the Karplus equation. For a dihedral angle of 180 degrees, you get a coupling constant of 15 hertz. Again, you can also do this with your model kit. Do the Newman projection. There's HA. There's your methyl, there's your HB, there's your equatorial tert-butyl, and you have the rest of the chair. You can fill in those substituents. So HB HH. So we can see that 180-degree angle from the Newman as well. So which butene derivative will have the most energetic eclipsed conformation? So you can basically draw these out. They're all butane. So there's 2-methylbutane. There's 2,2,3,3 tetramethylbutane. There's 2,3-dimethylbutane, and there's 2,2-dimethylbutane. So really, choice B is the one where it's eclipsed. You're going to have all methyl-methyl eclipsing, so that's going to lead to the highest energy conformation of all of those choices. So what about the staggered conformation of that compound? Basically, it's going to look like that. So you have 1, 2, 3, 4, 5, 6 gauche penalties to pay. So 6 times 3.8, that's going to get you your 22.8 kilojoules per mole penalty for that. What is the name of the molecule shown? So you have 2-fluoro-3-iodobutane. We're going to do our Kahn-Ingold Pralog here. So fluorine's 1. This carbon bearing the iodide is 2. This carbon's 3. The lowest priority group is back. So we're going to get 2R since we're going clockwise. Then for the other carbon, the iodide gets priority 1. The carbon bearing the fluorine is 2. The other carbon's 3. We're going clockwise there, but since the H is towards us, we flip, so that's 3S. So 2R, 3S, 2-fluoro-3-iodobutane. So 2R, 3S. And finally, the last question says, for that molecule, how many total stereoisomers? You have 2. The stereogenic carbons, 2 to the 2 equals 4. The answer is D. And if you look, they're all listed here. So 1, 2, 3, 4. Those are the names of those 4 stereoisomers.